thank Colin and the organizers for the invitation. I am honored to the point of being humbled by being here. So I'm very, very pleased to be here at CSD 50 because I'm not a crystallographer, but as they say in one of the commercials back in the States for medicines, an actor comes on and he says, I'm not a doctor, but I play one on TV shows. So that gives him credibility. So I'll just leave it at that. So I'm really pleased with the way the talks have turned out today because they dovetail very nicely together. So I'm going to be talking about the use of crystallography data, and the first part of my talk will be talking about its use in force fields. But before that, science, we can talk about data, we can talk about databases, but really science is about people. And so there are lots of people I could have on this slide, but these are the people that I primarily worked with closely that basically taught me crystallography. I did my postdoc work at the Naval Research Lab in Washington, and Judy was quite a good mentor. How many people here know Judy Flippin Anderson? Yes? A few people, yes. I know Olga knew her well as well. Cliff George, probably no one heard of Cliff George. He's published lots of papers, but he never got out of the lab. And then, of course, Jerome and Isabella. They always went to the conference room every day for lunch. Anybody who wanted to join them could, and I joined them most days. I heard lots of good stories. Arnie Hagler, I talk about a lot. I worked with him very closely during my postdoc, as I did with Don Williams. Jack Gugatas was a crystallographer at Bristol-Myers Squibb. Anybody here know Jack? Yeah, okay, Jack's a great guy. He would yank me into his office every now and then as I was walking by, and he'd show me some great, new, interesting things that he was working on, because he was often brought in if there was formulation issues. So he had some really curious cases. Let's see. And then there's Schneur Lifson, who I'll talk about a lot also. And then, of course, there's Jack. Now, Jack, I never had the honor of working with him, but I did find out about 25 years ago that 5 minutes talking with Jack was more illuminating than oftentimes, I was going to say years, but at least days or hours talking with somebody else. So I was always very pleased, and I can never think about a polymorph without thinking about Jack. So molecular modeling, in many ways, it is one of the most fundamental technologies in computer-aided drug design. And what I do is primarily computer-aided drug design, working to develop new drugs. And the force fields are the mathematical engines of molecular modeling. And remember that one of the reasons we do force fields in molecular modeling is because we can't afford to do quantum. So I just try to keep that in mind, because we're trying to do something very quick and very simple on a problem that's very complex and takes a long time. But I found it very interesting, and this is how I learned about force fields, is that at least the early force fields relied heavily on crystal structures, both for derivation of the parameters and then for validation of the force fields. These derived parameters, especially some of them coming out of Lifson's lab, were propagated to many different force fields, and some of these were developed back in the early 70s, and I have no doubt that some of them are still in force fields today. And it's really great literature to read some of these papers, because it was really a time in which people were beginning to understand structure, beginning to think about it, beginning to relate crystal structures with solution structures, with the modeling they did. They really thought about the details of the calculations they were doing and the force fields they were developing. So Schneur, I can't say enough good about. I've once introduced him as the grandfather of the field of molecular modeling, and you'll see why. It wasn't meant as an insult. But he published lots of papers. And I couldn't put them all up here. I put all of them that I could find that dealt with force fields. And I had left out a lot of content, or these things would be very busy slides, but I have the title here. And then the interesting people that published with him. And here's one from '67 that Jack worked with him. Was this the one you mentioned last night at dinner, or did I miss a paper, Jack?
Well, the paper, yeah, it's definitely that of a composition that you must have had about 65.
I see. Okay. And then many people, probably those of us, especially computational chemists, know, or anybody who follows the Nobel Prize winners knows Airy. In fact, Schneer once time told me that Airy was a very unassuming person until Schneer had to force Airy to realize how intelligent and how smart he really was. I took from this paper, I just saw this statement here, which I think was very interesting, because they were talking about the force field and what the structure they calculated, and they said, well, it disagrees with the conformation of the crystal state. And there are still some people nowadays that think, well, you get the crystal structure, that should be the structure you're going to use all the time. But then they go on to say, it's folded in the opposite directions, but it does agree with the suggestion of Snellman and Nielsen about and there's solution structures. And it's kind of interesting to see this thought process back when people were still trying to understand what conformation meant and how it could vary. So Schneer had lots of papers, and here in the early 70s, Arnie came into play. I don't know how many people know Arnie. Arnie was the founder of the Biosim company. He also developed, helped with Schneer-Lifson develop the CVFF force field, and then went on to develop the CFF force field. And then some more papers from Schneer's lab, with many from Arnie, and then also Michael Levitt was another one of the recent Nobel Prize winners. So you can see, this was really quite an incubator of talent, even more so because it turns out, I found out just recently that Martin Karplus and his wife at that time, Susan, spent a year with Schneer. And so God rest his soul, I wish I could talk again with Schneer. I didn't spend too much time with him. I spent several days at one point, and he had lots of good stories. Now, Don Williams was at the University of Louisville. He was very sort of an unassuming kind of guy. I don't think he ever had more than 1 or 2 postdocs at a time and did lots of work. But he developed, from the early days, he started out as a crystallographer, developed potential parameters for many things. He really took a very good physics-based approach to this. He and one of his students, Starr, developed the Williams Starr potential that many people, especially I think in the crystallography community, used. And he just had lots of good papers for developing primarily non-bonded potentials. He also did a lot of work. He had his own PK, what he called PAC 83, I think, a program for trying to predict crystal structure and crystal polymorphs. I had the pleasure of having him work with me during my postdoc work, and we were developing and testing force fields for lipid molecules. That you'll see in just a few slides, I used very heavily. And then he taught me this wonderful story about spherical and asphericity and sphericity in atoms. And in most of the molecular modeling community, people think an atom is round. It's easy, right? You have point charges, you calculate distance between them. You don't have to worry about nasty things like anisotropy. But when I saw this, I think I've got to start listening to that. And then Sally Price, also some of her papers, really got me thinking about this and getting kind of scared about some of what we were doing with some of our force fields. Now that comes back to Arnie. You saw all the papers that Arnie had with Schneer. He went on to do more papers. He sent me these 2 recently, and he thought that he said these were very seminal. But I said, well, Arnie, tell me, I want the papers where you used crystal structures for force field development. That was this. So there's 25 here. There was a massive effort at the company Biosim to develop force fields. It was a consortium that had about, at one time, from almost 30 members in it from industry and academia who were participating in developing a force field, primarily for an internal force field, for trying to develop parameters and a form that would cover a large range of drug space, a large range of the functional forms and functional features that weren't participating in drug design. And so I think it was quite a successful effort, and it gave rise to this series of CFF, consistent force fields. Now, Arnie being Arnie, when I asked him for some references, he said there are others. There's so many others out there. You have to mention these. I was emailing with him last week, but unfortunately, by doing this now, I'm excluding so many other people that I wish I had up here, right? Because I thought, well, I'm going to play it safe and play it easy and just put the people that I'd worked with here. But he mentioned these, and of course, Angelo, I had forgotten him, so I wanted to make sure that he was up here as well. And here are other papers. But I wish I could talk about each and every one, but we'd be here for a long, long time. So curious, I've known lots of people who develop lots of force fields. I talk to them all the time, and I said, well, why? Are you simulating crystals? Are you seeing whether or not they work in crystals? Oh, no, we're not doing that. Well, why not? Well, the crystal lattice is artificial. They're atoms interacting with atoms. Now, after Robin's talk yesterday, I thought, well, maybe they're not as relevant to protein structures as they are to others, but I think there's got to be some statistical issues in here, too, but I'd like to talk to you more about that, Robin. They're not relevant to biological interactions. I mean, the density of crystals isn't all that different from the density of small molecule crystals, not all that different in many cases from the density in biological systems. Not that we really know the density of a lot of the biological systems. They rely on quantum mechanics, which is sort of implies that vacuum conformation is better than a condensed phase conformation. Go figure. Some do a very good job using liquid structure because there's a lot of data that can be gotten about that, and it's very useful. And in my humble opinion, both liquids and crystals should be used. The one that really gets me is because they can't. Well, I can't do that. Why not? Oh, my program doesn't do crystal lattices. It's like, well, rewrite it. You know, it's just such a weak reason for not doing it. Now, but there are still, no matter how good the force fields are, there are still caveats and concerns. Many of these force fields many are available, right? Lots and lots of different ones in different programming packages. And people, you know, they just want a number. And I'm not really being critical of them. People have a big job to do when they're designing drugs. And if they spent a lot of time thinking about every angle, every bond length, every torsion, they would never get where they needed to go. On the other hand, just pushing a button and hoping the result or assuming the result is the right one is not a good way to do it anyway. And then some force fields are developed for particular purposes. And so I think most users nowadays don't do that. So I'm talking about users that use commercial software that you've all heard about that you know, people pay lots of money to use from some of the big software houses. I'm not criticizing anybody at the software houses or their science. It's just that people then use it as a black box. And then these force fields, the companies are oftentimes improving them almost constantly. But still, in most cases, we don't know what the accuracy and precision and the error in these force fields are. Now, one of the advantages for me participating in Hagler's force field development effort is that we would sit down for meetings and we would be there for days looking at each and every bond angle, and torsion, and non-bond interaction that they were parameterizing. So we got the chance to see how they were, and it was one of the first efforts that really applied a real statistics-based approach to developing force fields. And so we did get an index of error on different functional groups. And one of the places that's the most difficult, as I'm sure everybody knows, is at torsion potentials. And sometimes they can be difficult to fit. And many times people want to use a very simple analytical approach to doing this. So this is just what you expect. This is the torsional profile of rotating around the carbon-carbon single bond in ethane, and nice and regular and all that. And a lot of force fields try to get the minimum energy. People talk about minimum energy a lot. Maximum energy they didn't used to try to get because it wasn't relevant at one time. It is relevant now when people do molecular dynamics. But in reality, biology isn't so much about min and max. Min is nice, max is important if you're looking at time-dependent properties. But we are dealing down here, which is curiously enough, where we get to see lots of structures from the CSD. And if we blow that up and take a look, sorry, this is busy, it was used for two different purposes. Really what we're talking about is KT, right? There's thermal energy out there. All the molecules have this energy. They're not going to hang around in the minimum energy state. They're going to bounce around. And KT is about up here for biological systems. And you can see we have quite a nice spread of angles here that are important. And we have to take that in consideration. And our force field, our torsional potentials have to take that into consideration as well. Now, if you look at some torsions, some of them are not pretty. You know, ethane was pretty, you know, ethane's simple. But I've seen some profiles that people have calculated by quantum methods or others that were really kind of, you know, not nearly so regular. And this is, both of these are really mock-ups of what I've seen. Because if I didn't have mock-ups, I'd have to use somebody's actually stuff and then reference them, and that might not look good. But here's something that was related to a potential that I saw somebody could do, and it was it was a complex system. I just mocked this up. But if this was the actual curve that they saw, their force field gave them something like this, and they said, well, the min is pretty good, the max is pretty good. Then I thought, well, what's happening here? And now this was developed for some other purpose, so we should really be probably thinking about further down here. But you can see there's quite a gap here. I mean, this is much steeper. It means that we're not going to sample quite the way we would normally sample if we're using this red versus what we assume is the standard, which was from high-level quantum mechanics. Or from experiment, and we were off probably in this area about half a kilcal per mole, and some people say it's half a kilcal per mole. Why are we worried about that? So what? Well, nature doesn't throw away half kilcals, and also drug discovery operates within a realm of usually about nanomolar to micromolar. That's where we have our lunch, and it's equivalent to only about 4.5, a little over 4 kilcals per mole. But drug optimization is even scarier because it usually operates in the realm of about 5 kilcals per, 0.5 kilcals per mole. So we really have to especially get that lower part of the well of the torsion right. We want it right energetically, we want it right structurally, because that's the playground that we're working in. So along these lines, there's a project at Bristol Myers Squibb trying to block the endothelin receptor, and this was for cardiovascular. Endothelin is a potent vasoconstrictor. This is the endothelin peptide that binds to this GPCR. And we wanted to get a handle on this, and our chemists were having a bit of a hard time. Now, this is old work, but it is work that was, first of all, published, and second of all, that I can talk about. And the chemists came to us with a bunch of structures, all of them these aryl sulfonamides. Now, what I understood from working with Hagler and from his force field effort was that this was a real bear to parameterize. And so I thought, as much as I respected that force field, I thought, well, maybe that's not the best way to go. I need to get some validation, which I would typically do if I looked at a structure and it didn't look right, which is probably not the best way of evaluating quality. I would go, where would I go? I would go to the CSD, and I would pull out as many structures as I could. I would always, too, make my search deliberately broader, so that I would have an excuse to go through a couple hundred structures and look at them, because they're pretty, let's face it. But also it was so neat to see these things. I'd want 1 or 2 structures, but I'd look at 100 of them and I'd think, wow, this stuff can really work. This stuff really exists. It's neat stuff. And so, of course, I went to the CSD, and for these various torsions, extracted a good distribution of what the angles could be. And we could have developed a potential based on this, like I think Martin mentioned earlier. In reality, we just set them basically roughly to these coordinates. And so we generated the 3D models based on those conformations. And we did an approach of ligand-based drug design called COMPA, which required us to overlay the molecules. And then we applied them to this COMPA approach. We also used them, as you'll see, for other purposes. I could spend longer on this, but my time is probably getting close to running out. But the molecules did 2 things for us, or these models that we got very good predictions based on these models. Now, was the CSD responsible? Sure, why not? The other thing was we independently, we had an orthogonal project to model, again, this is way before we knew much about crystal structures of GPCRs, to model that particular GPCR. We had a mass of mutation data at Bristol Myers for this. Much of that's published. And we generated a model of this, and in that model, the molecules were docked to see how well they would fit. And when we aligned the ligand-based results with the structure-based results, the results came out, spot on. So that was another convincing piece of data to justify our use of the conformations that we used. Now, sort of closing up on my examples, anybody who's known me for a long time, knows that I spent a lot of years looking at membrane structures, and with an aim of trying to understand how drugs interact with biological membranes. So this is simply a lipid bilayer with water on the top and the bottom. Is yellow, and yellow are the very highly charged lipid head groups, and then these are hydrocarbons here. And so I wanted to simulate this system. And I thought, well, where am I going to start with this? Well, fortunately, at that time, there were crystal structures of this, and then I found a crystal structure of all of it. In fact, there were some folks, I think all of them were, or at least some of the authors here were at the ETH, being very prolific. Helmut Hauser, I'm embarrassed to say this is Erwin Pascher, quite a few structures of relevant molecules for what I did. So I spent a lot of time looking at these, looking at how they, at what they meant for us, and then also using those to develop parameters, and then especially to validate parameters. And so that's what we have here, a validation study using on these lipid crystals. Don and I went further to look at that, validated it both through just static modeling, but also through dynamics, because that's what we wanted to do. And then we went on to develop parameters for other things. But, and I'm not sure I've mentioned about in terms of Arnie's papers for the PEFC, but every one of those employed crystal structures for validation. So that was a big part of the project. Anytime we wanted to the effort wanted to parameterize a new functional group, they looked for that functional group within the CSD, and then you used that data for either derivation of parameters but especially for validation of parameters. And so based on starting with those crystal structures, doing the simulations, allowing the system to evolve, we were able to study things like the placement of drugs in membranes, the permeation of drugs through membranes, which you see here some free energy profiles from those studies to show the likely placement throughout the membrane. And then we were probably some of the first groups, from some of the first people to actually study proteins in membranes as well. So I thought, well, what's the advantage of starting with crystal structures? What was my leg up? Well, my leg up was starting with crystal structures was a heck of a lot more work than some of my competitors was doing. So that's an issue. But that work meant dealing with the physics of it, dealing with trying to get things right from the start. And so my work was driven by physics, not by hypothetical modeling, whereas a lot of my competitors, they would actually start with a model of what they thought a membrane should be like. And so it looked really good to start with. They ran it for five nanoseconds or something, or no, actually not even that, much less than that. A very short period of time, and it looked good. So then they published it. But once they ran it for a nanosecond, it started to fall apart. In my case, we started with the crystal structures, and we allowed the simulations to evolve. And if the simulations didn't evolve, we know we had something wrong with the simulation. We knew how to fix it. So that took us some time, but our simulations then basically essentially worked from the start. They didn't degrade. We didn't use up a lot of computer time otherwise, and we were able to have some of the first simulations of real lipid molecules in a biological membrane, in a lipid bilayer. So those are my examples. That's some of my praise of the CSD is the fact that this data is out there and allowing us to use it. But I also now realize some of the issues with force fields. So I have 3 wishes here. So, you know, you're not getting away with just congratulations, it's 50 years. I'm expecting some more. I'd love to see something very much like Martin had mentioned, where when somebody gets a structure, it would be great to have this integrated into all the software. And so when somebody generates a model from a force field in a program, that it also does a check with CSD. And, you know, if everything's okay, maybe that's okay, just leave it as is. But maybe, you know, provide profiles or provide some alert that maybe this is a little off from what we see in the CSD. Might be right, might be wrong, don't know, but at least it's food for thought. At least people are thinking about it now. And at least they can say, well, you know, this study didn't work out, but I do remember I had this alert that, you know, there might not have been right. My model might not have been. I think I'm going to go back and check that. Maybe I can do better. And so, you know, you can have lots of plots and charts or whatever, but maybe you can just start out with just an alert, you know. Hey, you got problems, you know, you got to do something about it. You know, make it really bold so people will stop and think about it. So, for instance, you know, some very authoritative figure. So, you know, if it doesn't work, you know, have that Roman emperor up there, you know, putting his thumb down, making people squirm, you know, this isn't going to work, just don't do it, you know, don't go any farther. But of course, if it works, if the force field works, give credit where credit's due. You should have another authority figure that's saying, you know, this works, this is good. So maybe something like this. You know, hey guys, let's do it. You know, it works, go ahead, let's go out and have a beer, and everything is fine. So my third wish is I think we need more education. So I, and then the people I work with especially, when a chemist or someone is trying to design a new drug, they are dealing with dozens of pieces of information at one time for each molecule they're dealing with, and they might be dealing with dozens or hundreds of molecules. Lots of the data. You know, we can say, geez, they should understand the data, but it's just too much for anybody to absorb. All of you out here are experts. You know what you don't know about your expertise. Somebody who's not an expert has no idea. So if there was a course where somebody could start to get some feel for how the data was derived, the precision, the error, the caveats, what mistakes might be made, that would be great. It would also really have software that prevents structures that do provide information. So much software now, if you ask for, sometimes it doesn't even ask you what PDB file you want. You give it a sequence of a protein, it'll go out and decide what protein you should use. It gets it out of the protein data bank, it puts it up, and all that very interesting, very important data that has been annotated that's in the MMSIF files, the user doesn't see it at all. There's no, that software doesn't give them that information. So you know, they're, or it doesn't give them any caveats. So again, I'm talking now to the software developers. Any software developers here? Yeah, 1, 2, okay. Well, I mean, like commercial out there, you know, Schrodinger types or anything like that. I'm not going to be lynched or anything. Okay, all right. So it'd be great to have that presentation. And sometimes even just quick rudimentary information can help. So I think a really good example of this is a course that Helen put on at the PDB a few years ago, crystallography for modelers. She was kind enough to let me participate in organizing that. When we first started setting it up, I thought, you know, it's going to be, you know, 10 people from somewhere in the New Jersey area. As it got to the point that you know, it was over 30 people. Part of it was hands-on. We didn't have enough computers to suggest to have everybody be hands-on, so it had to be closed down. But there were people from Mexico. We had, I think, somebody from Finland. We had, I don't know where everyone came from. And in the end, the people were really thrilled with what they learned. The part that they liked best was there were 2 crystallographers there. There was a section on refinement, and these crystallographers would talk about how they did the refinement. These folks had no idea. I mean, so many people think that for any crystal structure, I'm talking here about protein crystal structures, but small molecule as well, you know, you take the crystal, you throw it in the machine, you push a button, data comes out, and it is the tablet from God on the mount, right? And you know, and they have no idea what goes on. And what a lot of the audience really liked was these 2 crystallographers talking about the method of refinement, which was somewhat different. And they said, well, what's the right way to do it? Well, what do you use? And the fellow says, well, I like to look at the maps from 2FO minus FC, or forgive me, I'm not a crystallographer. So, and they went, well, what do you use? Oh, I use like 2FO minus, or 2FC minus FO or whatever. Well, which one's right? Well, And well, how do you get this? I mean, doesn't it all just fall out? It doesn't fall out. It's hard work in many cases, right? So anyway, this is a great course. It'd be nice to see it duplicated. And then finally, congratulations to 50 years. Thank you for 50 years. I hope for more 50 years. Thanks for progressing, helping us to progress molecular modeling, and really thanks for helping us to progress drug discovery, because it has really been an essential resource for us.